We're still looking at example 3. Now we're looking at part D. Part D, part E, and part F all deal with vertical axes of revolution, so the setup's going to be a little bit different. We've got our diagram drawn. If you haven't drawn your diagram yet, please pause the video now, draw the picture, and then play when you're ready. When you have a vertical axis of revolution, we're going to have to do some things a little bit differently. Here's what we're saying. They told us that the y-axis is going to be the axis of revolution, so look at the y-axis. X equals 0. The equation of the y-axis is x equals 0. Now you notice how this starts with x equals. That means we're going to want all our equations in terms of x equals. So look at our curve up top. See, we have y equals x squared. Well, let's get x by itself. If you square root both sides, we're going to get plus or minus root y equals x. Now let's identify what these parts are. A plus root y represents when x is positive, the right side of this curve. And minus root y represents when x is negative, the left side of this curve. Well, you can tell in this particular problem we're only dealing with the right side. So for this problem, we're going to say that x equals, we're going to say that x equals positive root y. Okay. And now let's try to determine what type of solid we'll have, what type of cross-sections we'll have when we rotate around the y-axis. Now we're going to have discs or washers. Well, if you see this blank white space in here between the shaded region and the axis of revolution, that's an indication that we're going to be dealing with washers. So we're going to need two radii. A big radius going from the axis of revolution to the far end of the shaded region, and a little radius. Let me relabel this here. Put R down here, and the little radius that will go from the axis of revolution to the near end of the shaded region. So let's get started. Remember, now we're talking about R of y. Like they say in French, R of y. And we're going to do something a little different to determine the expression for our radii. The expressions for our radii. Instead of top minus bottom, now we're going to do right minus left. So look at the big radius. On the right side, we have 2 minus, and on the left side, we have x equals 0. So big R of y is just 2. Now let's find little r of y. Little r of y. On the right side of the expression, we have our curve. And some people are tempted to write x squared here. But remember, everything's in terms of y now. So we'll write root y minus, on the left side of our radius, is defined by x equals 0. So the little radius is just positive root y. Okay. Now let's set up our integral. The volume is going to be found by taking pi times the integral. Now here's where we have to be a little bit careful. Since we're integrating with respect to y, we need y coordinates of this region. The lower end of this region is defined by y equals 0, and the highest point on this region is defined by this point. When x is 2, this is kind of scribbled. We write it over here, 2 comma 4. So 4 is the upper limit of integration. Okay. So we integrate from 0 to 4. The big radius, 2 squared, minus the little radius, root y squared, all with respect to y. At first, this idea of rotating around a vertical axis seems a little bit weird, but with a little bit of practice and a few more examples, things will get cleared up for us. Okay. We're going to go on the next example, but to have a little more room to work and to write a little more clearly and legibly, I'm going to go to scratch paper, and you can go to the note packet or scratch paper, whatever you're comfortable with. Okay, problem number 3, example E. We've drawn the diagram on scratch paper so we can write a little larger and have a little more room to work. This time they told us that we're dealing with the same area, the same region as before, but the axis of revolution now is a vertical line x equals 2. So let's determine if we're going to use disks or washers. Take a look at the axis of revolution in the shaded region. Is there any blank space in between the axis of revolution and the shaded region? If the answer is yes, then we're going to use washers. If the answer is no, well, then we're going to use disks. In this case, we're going to use disks. So we only need one radius, r of y. Let's determine r of y like so. We're going to draw a segment starting from the axis of revolution somewhere in the shaded region to the end of the shaded region. There's our radius segment. Remember, this time we do right minus left. So what bounds the right side of this radius segment? The horizontal line x equals 2. I'm sorry, vertical line x equals 2. Now minus what bounds the left side of our radius segment. Well, in this case, it's the curve. Remember, we can't write x squared in here because we're writing our function in terms of y. And when we got x by itself earlier, we saw that this curve is defined as x equals the square root of y. So when we put in the left side of this radius function, in the right minus left, we're going to write the square root of y. Okay. Now, just a reminder, points. Down here we've got the origin at 0, 0. In this corner, we've got 2, 0. And up at this intersection point, we've got 2, 4. So we're going to set up our integral like so. The volume is going to be pi times the integral. Now, again, be careful. The y values at the lower end of our region is 0. And the y value at the upper end of our region up here, at the top of the shaded region, is 4. So we're going to integrate from 0 to 4 with the radius function squared with respect to y. The radius function we found was 2 minus root y. This will be our setup for example 3, part E. Hopefully things are clearing up just a little bit. We're going to look at part F together, see if we can make sense out of this idea of finding the volumes of solids of revolution. Okay, taking a look at part F, you can see we've got the same region we've dealt with previously, and now we're going to rotate this region around the vertical line x equals 4. Let's determine if we're going to use disks or washers. What do you think? Well, if you said washers, then you're correct, because there's a big white space in between the shaded region and the axis of revolution. If we were to try to draw this 3D model, that blank space would indicate where the hole is that was drilled through our circular cross sections. Okay. 2 circles, we need 2 radii, a big R of y and a little r of y. So let's get started. To find the big radius, we're going to draw a segment from the axis of revolution to the far end of the shaded region. It's big R. Now let's set up our expression. What is it that's at the end of the right side of our radius segment? Well, it's a vertical line x equals 4. Now minus, what is it that's at the left side of our radius segment? Well, it's the curve. And in this case, the curve is expressed as x equals root y. So there we go. Now let's find our little radius. To identify the little radius, we're going to draw a segment from the axis of revolution to the near end of the shaded region. Okay. What's on the right side of this little radius segment? 4. The vertical line x equals 4. What's on the left side of the little radius segment? 2. The vertical line x equals 2. So little r of y can be simplified to just be 2. The little radius is constant. The big radius is variable. Okay. Now let's set up our volume integral. Remember, the volume is going to be pi times the integral from c to d of big R of y squared minus little r of y squared dy. So let's get specific. In this case, our volume is going to be pi times the integral of 0 to 4. Remember, the bottom of our shaded region is at y equals 0. The top, the highest point of our shaded region, is at y equals 4. And now, let's set up our integrand. We're going to have the big radius squared minus the little radius squared with respect to y. The big radius is 4 minus root y. The little radius was 2. And there you have it. This is our setup for finding the volume of the solid of revolution generated by taking the region defined in example 3 and rotating that region around the vertical line x equals 4. Hopefully this is clearing up a little bit for you. Do your best on the homework assignments. We're going to talk about this again in class next time. If you think you understand how to do these problems, try to do example 4 on your own and then compare with the videos. We're going to make another set of videos for example 4. They might not be uploaded right away, but they'll be uploaded sometime soon, and see how we do. Well, thanks for watching the videos. Hopefully you found them helpful.